In this video, I'm going to be talking about nonlinear regression. Specifically, we're going to do regression for exponential and logarithmic and power functions. I'm also going to talk about linearization, which is a way that you can see which of those models is actually going to work for your given set of data. We'll be using an online electronic tool called Desmos. Now, Desmos has an online graphing calculator that we've been using this year. You go to desmos.com, under their math tools, choose the graphing calculator, and you'll get a window that looks a little bit like this. I have typed in my tables already just to save time in the video, but I'll show you how to do that. And if you're typing in a table, you can pause the video if you want to follow along, which I recommend. Pause the video when you need to type in a table, and that'll give you time to type it in yourself, so you can be doing the things I'm doing. To actually enter a table, when you're typing in something new into Desmos, if you click on this plus button up in the corner, it will give you a few different options of the sorts of things you can type in. You can choose table from the list. Now, Desmos will automatically label it with the columns with variables. You can change these somewhat, although depending on what you change them to, Desmos might complain. You'll notice this one has a subscript 5. It's actually my 5th table. I have a x1 table, an x2 table, 3. I've got 4 tables typed in. Each table needs to have a unique subscript so that they don't interfere with each other in Desmos logic. You can type in the table then. Pushing tab will move you from one piece to the next. That way you don't have to move your mouse around a bunch. I'm not going to type in the whole table. You can see how it's going, but I've already got it, so I'm just going to delete that one and move on to this table. You can turn the plotting points on and off for a scatter plot like this, but we can't see any of the points here because we're still on the home screen from -10 to 10, and the numbers here for y don't start until 400. You could zoom manually using the zoom in and zoom out, and this one will let you adjust your x and y axes separately. But if you have a table put in, there's actually a zoom fit icon down here, and if you push that, it'll automatically set your x and y axis so you can see all the points in that particular scatter plot. These points are slightly curvy. In your book this year, some of the questions will tell you which type of relationship, and some of the questions will ask you to pick the best relationship. This one here, it really, at this scale, it looks to me like this could almost sort of look a little straight. So if I zoom in on the y there a little bit, it'll accentuate the curve, and it makes it clearer this is actually curving, not straight. Given that we know this is exponential, then I can get Desmos to find the best exponential fit that it can. I'm going to start by typing in the y variable. Make sure you put the correct subscript. If you're going to do regression, you need that subscript from the appropriate table. To let Desmos know it's going to be regression, I need to use the tilde. Now that's the squiggly line. You'll find it underneath your escape key, usually above your tab. It's just one squiggly line. It means approximate, and that's how Desmos knows you want regression. The basic format for a basic parent function for exponential here, our basic format is a times b to the power of x, but make sure you put x1 so it knows which table you're talking about. And once you get that typed in, Desmos will automatically pick an a and b that are the best fit for your table. And as you can see, this exponential function here is really good fit. In fact, this r squared value will give you an idea of how good the fit is. An r squared value of 1 is perfect. That means the curve goes exactly through every single point. Numbers close to 1 are very good. The further a number gets from 1, the worse the fit is. If you're down around 0.9 or lower for this assignment, it's probably not the right thing, not what you should have been doing. Although there are situations where 0.9 is acceptable, especially if what you're doing is linear. Sometimes the statistics just aren't better than that. We're gonna demand a little bit more precision. Most of the examples in your book you're gonna expect values really close to 1. So Desmos tells me what a and b should be. A is around 400, b is about 1.19, and so I could write those down. We could actually create a function using those values if we wanted to. We can actually use a and b again in Desmos if we want to without redefining them. So I could create a function here, f of x, and if I use it, I can actually find other values, like say 8. And it will automatically put them in using the a and b it's picked, and it'll give me the y value that goes with them. So it can be useful for predicting other values. That's something you can do. But here's the exponential model, 400 times 1.19 to the x. That's my exponential regression model for this table. I want to move to this next table. Turn this off. These are difficult to see the relationship here. They're much smaller than the ones I started with, so I'm going to zoom again. And you see here, this one's going down, which might be exponential growth, except I happen to know this is meant to be a logarithmic relationship. If I switch these to my new table, y2, x2, 2, we'll see it's not the worst fit, 0.92, but it's not a very good fit. And if I plot this, the curvature doesn't really seem to match at all. So what I'm right, as I said, this is meant to be a logarithmic model, for which our basic form is a times the ln of x plus b. You see, that really looks much more comfortable as a fit here. Not to mention our r went from like 0.92 to 0.99. This is a much better fit. So we're looking here at negative 6.7 times the ln of x plus 72.3. And that's our logarithmic function of best fit. It's logarithmic regression then looks like this. Moving on to my third example. Let me zoom to it. These numbers are quite big. Now looking here, this looks, this is meant to also, this is meant to be one where you have to figure out which type of regression it is yourself. Looking here, logarithmic is probably not going to be a good fit. In fact, I'm pretty sure it won't do backwards logarithms. Like if I'm trying to fit a logarithm here, I'm assuming the asymptote's over here somewhere. But I don't think Desmos even does that. This is going to be laughable. Oh yeah, see, that curvature is all wrong. The fit is 0.66. That's terrible. I'm going to try also a power function, which we haven't done one yet. The exponential function, or the power function, is a times x to the x3 to the power of b. 0.98. See, that's a better fit. But I'm also now going to compare it to y3 is approximately a times b to the x3. And here you see this one is a way, this one's a perfect fit. This is an exponential relationship. So let me turn this one off. See, this one's actually exponential. This is another one of those perfect fits because I got r equals 1. So exponential function is the correct one to pick here. It's got by far the best fit of the ones we tried. And a is 1,000, b is 1.78. Okay, my last example here, table 4, is the one I'm going to use to talk about linearization. So looking at these numbers, let me zoom in. I've got a curvature here. I am pretty sure this is not logarithmic. Well, very sure. This is not logarithmic, but it could be exponential. So it seems like it's heading towards 0, which suggests a power function, but really a could be quite small. So I'm going to try what we call linearization. Now the idea here is we suspect this may be, say, an exponential relationship, and what we want to try is to neutralize that in order to force the points into a line, and that's why it's called linearization. So in order to neutralize the linearization, I want to take these points and I want to leave the x's the same, but in order to flatten these into a straight line, I want to do the opposite of exponential to my y, which means I want to actually take the logarithm of each one of my y's. Now, if you're using values from a table and you get the subscripts right, Desmos will actually take this, it'll plot with all of these x's, it'll plot one row at a time with these x's, but each y it will take, it'll do the ln of the y before it plots it. You can see it's done that down here. Now these These actually are slightly curved. They're pretty small though, so to really see whether it's curved or straight, I'm going to zoom in on my y. And you can see here, as you zoom in on the y, it becomes very obvious. These are actually not straight. This is a curve, which means what we were looking at here is not exponential. Because if it were exponential, this would flatten into a straight line. The other type I suggested was power function. Now the trick for flattening a power function is to actually take the ln of both the x's and the y's. And if it's a power function, oh, y to the fourth, if it's a power function, then when you flatten both the x's and the y's, what you'll get will be in a straight line, which this is. This is a very straight line. So power function is going to be the correct fit. There is a third option. Since we did some logarithmic regression, I'll talk about it. But if this relationship is logarithmic, in order to neutralize the curve, you do the ln of the x column because the y columns are already logarithmic. Now in this case, that's going to be terrible, or at least not linear. Let me zoom out a bit there. So you can see, same color. Let me switch the color on this one too. So you can see the original was already curvy, and doing the ln of x made it even curvier because it's not meant to neutralize an exponential relationship, it's meant to neutralize a logarithm. In fact, let me go back to our logarithmic example, which was table 2. So if I'm looking at an actual logarithmic example, and I do the ln of the x's and plot them against the y's, then what I will get will be pretty close to a straight line. You can see this one, this wasn't the best fit. It was okay. So the points are sort of in a line. They certainly don't seem to be curving, although they don't quite fit along the line. But these points were kind of above and below the line anyway when we did our regression. So that's not really surprising, but it is fairly neutralized into a line. So that's promising. There are other types of linearization, and you can look in your book if you want to see them. But now that I've done this example down here with my linearization, what we decided was the exponential was not a good fit because it produced a curve, but the power function produced a quite straight line. So what we're looking at here is a power function relationship. So the regression equation then, y4 is approximately equal to a times x 4 to the power of b. And you can see this right here looks like a good curve. It seems to be going through all those points. And in fact, r squared is 1, so this is another one of those perfect fit ones. A is 3, b is 3. This is 3x cubed is this power function here. Hopefully that'll get you started there in Desmos. You can mess around a little bit. Really, visual inspection will usually tell you whether or not something's a good fit. But Desmos does a good job of reporting your correlation coefficient here. Remember, a value of 1 is perfect. Anything close to 1 is very good. The lower the number gets, the worse the fit is. Contact me if you have any questions, and good luck.